Good afternoon once again, colleagues. It's 14:35 from where I'm joining from. Today is the 29th of April, 2026, and welcome to our webinar today. The title is Method Validation, Verification, and Measurement Uncertainty. So once again, this presentation is for educational purposes only. And while every effort has been made to ensure the accuracy of the information regarding ISO 15189 or any standard that we'll refer to, this presentation does not constitute official accreditation advice. Laboratories and participants should always refer to official ISO standard documents and their specific national or regional accreditation body requirements. The person presenting today is named Innocent Mdlongwa. He holds a bachelor's degree in medical laboratory sciences and a master's degree in clinical epidemiology. He's a consultant, QMS consultant with over 25 years of experience. He's a certified lead auditor for ISO 15189, specifically 2022, as we are currently implementing that standard. He's a SLIPTA auditor, a SLAMTA trainer, and has led multidisciplinary teams evaluate and assess laboratories in Botswana, Malawi, Namibia, Rwanda, Tanzania, Zambia, and Zimbabwe. And is very passionate about turning compliance into excellence, hence the webinar series that we've been presenting regarding issues to do with excellence in quality in laboratory services. And this webinar, as usual, is hosted by a company called CLISS Quality Advisory Services. And this is a company registered in Botswana, and we offer consultancy services in ISO quality management systems, strengthening for medical research and industrial labs. CLISS is an acronym which stands for Consulting for Laboratory ISO System Strengthening. And our name is our promise. We exist to hardwire global best practice into every test or calibration or every report that your facility produces. We offer end-to-end management systems consultancy. This includes ISO trainings. We offer, of course, the webinar series that has been running for some months now. We offer accreditation mentorship, gap analysis, risk management trainings, and root cause determination, guidance on root cause determination and continual improvement. As we start today's presentation, we want to welcome you, and we really appreciate the CLISS family that has been expanding day by day. So we did take a snapshot to check who is joining in. I think after advertising this webinar, we checked it 24 hours later. We had 367 participants that were joining in from 24 countries and 118 cities, which means really our family is growing bigger and bigger every day. This was at the 24-hour point, but just before the meeting, we checked and we were close to 700, like I said earlier on. We're close to 700 participants that showed interest in joining in today's webinar. And our footprint covers Zimbabwe, Ghana. We have a number of people from Ghana, Nigeria, Kenya, Zambia, the DRC, Tanzania, Rwanda, Malawi, Lesotho, Botswana, and slowly we are getting to the Asian market as well. We see people from Pakistan. We have people joining in from France. South Africa is coming in as well. Thank you so much for the support. And for today, we are going to distinguish between validation and verification. We are going to help you plan and execute your key validation parameters and also calculating and expressing measurement uncertainty. A closer look at the agenda. We will look at the foundations and key concepts. We will look at method validation, parameters and planning. We'll look at verification for routine laboratories. You will notice that today's focus is not just 15189. We did check and notice that we have a lot of people that are coming in from testing laboratories, from calibration labs. We have people joining in from animal health. So we're not just focusing on clinical laboratories this time around, but we are also spreading our wings to cover 17025 activities as well. We will look at measurement uncertainty. We will look at documentation compliance. We'll look at a few examples of case studies, and then we'll have a final question and answer session. And today, for any questions that are posted on the chat box, we'll allow anyone to respond, because I did check and I do realize and appreciate that there is quite a wide base of expertise from people that registered to participate today. So we're all scientists. Let's participate in responding to questions that can be coming from maybe junior scientists that are joining in today. So going into the foundations and the key concepts, we need to understand the analytical process, how the analytical process flows. Samples are collected, and then we have the pre-analytical phase. And some people may want to combine the two, sample collection and pre-analytical phase, as one broad phase called pre-analytical, which is quite understandable and correct. And then we have the analytical method, which is in the center of the analytical phase. We have the post-analytical phase. And finally, we have a clinical decision, or whatever decision based on the report that is produced by the testing activity. And we all see that the method itself sits at the core, and its quality determines the reliability of every clinical or analytical decision that is going to be made. So this therefore tells us that it is a very critical activity that we need to understand and be able to apply very well, because erroneous results lead to a misdiagnosis or wrong decisions based on the result that you have produced as a lab. And also regulatory requirements demand demonstrated fitness for purpose. We will define what fitness for purpose is in the next slides. And of course, we've always emphasized the issue of cost of poor quality, hence the reason why we are always emphasizing on excellence, 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 more than just compliance. Core definitions that we should take note of. Method validation. This is the process of demonstrating that the new or significantly changed analytical method performs as intended for its specific purpose. So this is a definition you will find from ISO 17511. So we need to know this definition and understand the emphasis here is on new or significantly changed analytical method. Method verification, on the other hand, is a confirmation that an established or published method performs acceptably in your lab with your equipment and personnel. So your method is adopted, validated, you receive it in your system, you now verify that whatever the manufacturer claims is also reproducible in your environment. Measurement uncertainty, a parameter characterizing the dispersion of values attributed to a measurement. It quantifies doubt about the measurement result. So this one is a definition from GAM, the GAM document from 2008, or the JCTLM document from 2012, I think. And then fitness for purpose, like I said, we need to define this one as well so that we ensure that we understand this fully as we carry out verifications and validations. The method meets the performance requirement specified for its intended use. And the goal of the validation and verification activity, we want to prove that the method meets the specified performance requirements. Okay, now validation versus verification. What are the key differences? Validation is mainly used by method developers and labs that would have significantly changed their method based on what they would have received from the developer. If you decide to change the method, then you're expected to carry out a validation. And verification is done by end users. The scope covers a full characterization of performance, and we will highlight the key performance factors that you would need to evaluate when you're carrying out a validation in the next slides. And then for method verification, it's just confirmation in local conditions, and you don't have to be as extensive. In terms of efforts, validation takes weeks to months before you can say this method has been validated and is now fit for deployment. Verification is rather shorter. It may take days to weeks, depending on whether or not you need to do some troubleshooting as you carry out your verification exercise. In terms of outputs, a method validation should come up with a validation report, which is accompanied by an SOP. In verification exercises, you already have an SOP based on what the manufacturer has shared with you, because they did carry out the validation, the full validation, and they determined the optimum volumes, for instance, for each step, how many minutes you need to incubate and stuff like that. Now you are using that SOP to then verify that what the manufacturer claims is reproducible in your specifications. And in this case, you will produce a verification report. In terms of cost, validation is extensive and very expensive. It requires a high investment. But in terms of verification, moderate investment, depending on which angle you're coming from and what sort of material you'll be using to carry out the verification. In terms of standards that we need to be aware of as we carry on with this presentation, 17025 outside clinical testing labs for testing and calibration laboratories, and 15189 for medical laboratories, which is what most of us are used to. And then, of course, there is a CLSI guideline EP15A3 for verification of precision and bias in clinical laboratories. This is a very critical document that I would encourage all of us to get, so we will be able to carry out our verifications thoroughly. And then there's a GAM document from 2008. This is a guidance to expression of uncertainty in measurement. It's a metrology guideline that has been around for some time. And of course, there's the EURAChem document that we need to familiarize ourselves with. The big question is, when should you verify or validate? In general, you validate when the method is developed in-house. Excuse me. Okay. All right. So sorry, I had to clear that from my screen. I'm sure it was blocking the slides. You validate when the method is developed in-house or there is a significant modification to an existing published method, or there is a change in the matrix or the analyte range. For instance, if the method is validated to be using a blood sample, and then you want to then change and use a saliva sample, for instance, then you need to validate that method to show that the method can still perform well using that different type of specimen. When there's a change in the measurement principle, and when there's a transfer of the method into a new platform rather than the one that was originally released by the manufacturer. Verification, on the other hand, when you're implementing a commercial and standard method, you verify, you don't validate, because it comes already with a validation report that you should be able to review. You verify when you're installing a new analyzer of the same model. You verify when you are onboarding a new operator for the existing SOP. You verify or verify after a minor instrument repair. So we're highlighting these things because these are common issues where you have a lab, you get into a lab that has been running for 10 years, they have a verification report that has been there for 10 years, but the instrument has been repaired several times with major influence on the testing, but still the lab would not verification report. So these are very critical that we need to highlight. So now going into method validation, the key performance parameters that you should be considering if you are going to carry out a full validation, okay? The first one is specificity, selectivity, linearity and range, accuracy, otherwise defined as the trueness, precision, limit of detection or limit of quantification, robustness of the method or ruggedness, matrix effect, and stability issue.
Is associated with clarithromycin.
Colleagues, let's try to keep our mics muted. Thank you. Okay, so those are the key parameters that you need to look out for, 8 of them. And when coming up with a validation, you need to prepare a validation plan. And this is what should be included in the validation plan. First, you need to define the scope, which analyte are you going to be processing? What is the matrix? What is the concentration range? What is the intended use? So that you will be able to then say whether the method is fit for intended use. What is the regulatory context that you are dealing with? And number 2, you need to select the parameters for your verification. And this should be risk-based. I know we've been talking a lot about risk. This also applies to 17025 and 15189. Emphasis is now on risk, even when selecting which parameters you'll be evaluating. You need to set acceptance criteria before you carry out the experiment. So this should appear in your validation plan. And this, again, should be based on the intended use. You need to then design the experiments. Tell us how many replicates you are going to be running, at what concentration, the number of days, and how many analysts are going to be involved in carrying out the experiments. Once that is in place, you execute based on the plan that you would have prepared, ensuring that you record all raw data and maintaining a clear chain of custody. You then need to look at the data, perform statistical analysis, calculate the confidence intervals where it applies, and summarize the results, drawing conclusions as to whether your validation is passing or failing. Once that is done, you then need to approve and update the SOP that you will then be sharing to say, based on this, this is how the method has been validated, and users should then be able to follow that SOP. Now we'll go a little bit into the specifics of the different performance characteristics that you need to consider. What I will say at this point, today's presentation is very technical, and it's a subject that cannot be addressed in an hour. We will touch a bit on the specific characteristics, but this course is also available as a 2 to 3 day training, and as CLISS, we are available if you do reach out to us to then deliver the course to your teams. But for these purposes of this presentation, we are going to touch a bit and define a few things. So in terms of specificity, we're looking at the ability of the method to measure the target analyte accurately in the presence of the components or interfering substances, in the presence of other components that may interfere with the testing method, okay? So in this case, we're talking about endogenous interference like the bilirubin that can be found in blood. What effect does it have on the measurement of the analyte that you are interested in? And of course, we know that hemolysis is very common, and in some instances, leukemia is very common. So you are checking your method to say, can this affect the final result that we are going to get? In terms of acceptance criteria, recovery within plus or minus 10% of the true value in the presence of interference is generally acceptable. So you are checking and introducing this interference and seeing how far they can go in stretching your method. Then we're looking at linearity and the working range. This is the ability of the method to produce results directly proportional to the analyte concentration within a defined range. And how you'll go on and carrying out a linearity experiment, you're preparing 5 to 8 standards across the range and analyze them in triplicate. At a minimum, you analyze them in triplicate. You want to make sure that if you're analyzing them in triplicate, you are able to then pick any issues and troubleshoot. Otherwise, if you're depending on just one value, you may end up disregarding results that were actually meant to be outliers. And then you plot the response versus the concentration. The concentration is known, by the way, it's a standard. And then you calculate the correlation, which is your R squared. Assess the residual plots for random scatter and check the definition, the deviation from the linearity in terms of percentage. In terms of acceptance criteria, your R squared, the correlation coefficient should be greater than 0.999, 0.999 and higher is what is expected. And then the deviation from the linearity should be less than 2 to 5%. Anything higher than that is a fail. Okay, and then the key ranges that you need to define: analytical measurement range. How far can we measure a particular analyte without diluting it? Clinically reportable range. Can we expand this with a dilution and report a result that is outside the AMR? So you dilute. If you dilute, how far can you stretch the range? The lower limit of quantification and the upper limit of quantification. Then you also need to assess the bias or accuracy. And this is calculated as the measured value minus the reference value over the reference value times 100. And you express it as a percentage. This is a very simple calculation. So you do your measurements, you have the measured value minus the expected divided by the expected and multiply that by 100. Very easy to calculate. Excuse me. Apologies, I had to deal with the noise in the background. I hope you can all hear me now. Can you hear me?
Yes.
Yes, we can.
Yes, thank you. Thank you. So we're looking at linearity, and we're saying the ranges that you need to define as you carry out the experiment, and we had looked at all of them. So let's continue. We then looked at the bias. Sorry, let me mute this participant. Michael. Thank you. Okay, then we're saying bias can easily be calculated by the measured value minus the reference value divided by the expected and multiply that by 100 to express it as a percentage. And what reference materials do you need? If you have money, you can use certified reference materials. Quite expensive, but it's the best approach. Or you can use proficiency testing samples. As labs participating in proficiency testing, you can use those samples to then calculate your bias. Or you can use spiked or recovery experiments. So you know the concentrations, then you spike samples, and then you carry out the experiment. And then, of course, you can also consider method comparison studies. We are going to look at that. We will introduce that a bit, method comparison studies later. In terms of acceptance limits, typically plus or minus 2 to 5% is acceptable. For clinical labs, we use the total allowable errors, which will then guide us as to setting the limits. But you don't just thumbs up the limits, you need to have a reference to say, this is what is going to be acceptable for me for this particular analyte. And this must be specified before you carry out the experiments. And then you need to carry out statistical tests for you to be able to draw proper conclusions. The typical test that you would use is the t-test, also very easy to compute. And it's something that we are able to share with you how it's done if we are delivering a full course on method validation and verification. Then there's precision. Precision is at different levels. You're looking at repeatability, intermediate precision, and reproducibility. Repeatability is the lower level where you are looking at a test that is carried out repeatedly by the same person on the same day in the same lab environment. And there's little variation introduced there. So your CV target is a little bit tighter. 3 to 5% is acceptable. Intermediate precision. So repeatability will be what some people define as within run precision. And then intermediate precision within lab, where samples are run on different days by different analysts and at times by different instruments. And here you see that you're introducing a bit of more variation there. So your CV target is slightly wider, 7 to 10%, because of the increased variability there. Reproducibility is at different laboratories and different conditions, and the CV target again goes a little bit higher. So this is reproducibility over different days, different laboratories, and all the different analysts that are involved in carrying out the experiment. The limit of detection and quantification, LOD and LOQ. The limit of detection is the lowest amount that of an analyte that can be distinguished from a zero value, from a blank, where we know there's nothing. So the lowest that we can distinguish is the definition of your limit of detection. In terms of limit of quantification, it is the lowest amount of analytes that can be quantified with acceptable precision and accuracy. So they are slightly different, but similar. So we need to treat them differently. Okay. In terms of robustness and ruggedness testing, so by robustness, we're looking at the capacity of a method to remain unaffected by small, deliberate variations in method parameters. Let's look at this example. A method is developed and the manufacturer tells you you need to add 10 microliters, right? So we are saying if you add 15 microliters, you are off. So what the manufacturer will do, they will do what I call checkable titrations to see how far you can stretch this method. If they say 10 microliters, a robust method will allow 11 microliters to still go through without affecting the result. So you're actually checking for this, because these slight changes can be a problem. Incubation, for instance, if it says exactly 10 minutes and 10 minutes is up when you're on the phone dealing with a tricky doctor, if you go over by 30 seconds, it should not significantly affect the results. So that way we are saying this method is quite robust. And we are saying in your validation experiments, you should be able to validate and tell us how far you can go above or how far you can go below without necessarily affecting the performance of the test. In terms of ruggedness, we're looking at now the performance when the method is transferred across different laboratories so that we make sure that we are still able to get similar results from different laboratories or different equipment brands or different reagent lots. So that's the concept of robustness and ruggedness. And you need to be checking for these as you carry out your validation experiments. In terms of setting acceptance criteria, Once again, this is done before you start your experiments. And you need to tell us the source of the limit. And here we are sharing with you a general guide, but you need to be able to show us a reputable source to say these are the criteria I'm setting, and this is based on this kind of a source. Okay, so as you can see, validation is quite extensive. You will not be able to carry out, under general circumstances, carry out ruggedness experiments, for instance, or robustness experiments to carry out those in performing your usual verification. So now we're moving on to verification, and we are giving you a practical strategy that is based on CLSI guideline EP15. Okay, verification confirms that the method as described in the manufacturer's package insert or a published SOP. Remember, we said the output of a validation is a validation report, which then informs what will go into the SOP, right? Remember, we said robustness, you checking if there are any slight changes in the steps. You are checking how far above and how far below you can go. So that information is published into an SOP that will then guide the end users to say, our method performs optimally under these conditions, and these are the steps that you are going to be following. So you are verifying that given the conditions, given the SOP that is published by the manufacturer, this method can perform optimally under my conditions. So the first step to verification is to obtain the manufacturer's data. It's always readily available. If you look for this information, you can find it. What the manufacturer claims in terms of specifications or what you will find in the instructions for use. Without these, you are not able to then draw proper conclusions from your verification exercise. Next, you would want to run precision studies where you'll be running controls and samples across 5 days at a minimum, and you are doing this in duplicate every day. And you calculate within run and between day CV, okay? So remember the 3 layers, the within run and across runs, between day or within lab, okay? And then you go on to carry out your bias or accuracy studies where you'll be comparing 20 patient samples against a non-reference method. So this is the method that you are testing accuracy for. You're running the 20 samples on the method that you are verifying versus the reference method or certified reference material that is run on the method that you are testing, because your CRNs will be coming with some values. And then you calculate your bias and confidence intervals. And then you need to verify linearity. So those are the 3 key performance characteristics at a minimum that you are expected to verify. And then you are using 5 calibrators spanning your non-AMR and confirm linearity within plus or minus 3 to 5% of expected values. Once you've done that, you compare your results with the claimed specifications and then accept within the tolerance limits, the set tolerance limits, investigate if they are not meeting the set tolerance limits, and repeat if you are still not meeting. In most cases, if you investigate, you'll be able to pick where the problem is. Maybe the method was not calibrated. Maybe there was already some bias that was picked through your IQC before you even started your experiments. So you should be able to pinpoint where exactly the problem is before discarding the method. And then in terms of guidance from EP15A3 for precision, like I said, 5 days, 2 levels, 2 replicates. So you're running your low level and preferably your high level as well. That's at the minimum. If you have 3 levels, the better. You run your low, the medium, and the high. And then you calculate your within run SD and your between day SD. And the total SD will be the within, the square root of the within and the square root plus the square root of the between. So now you are able to then calculate your total SD. Okay. And then some statistical analysis there where you will be using the F factor based on chi-squared ratios. Again, this is deep statistical information that we'll be able to explain further if you participate in our 2 to 3 day training on method validation and verification. In terms of verification of bias, a minimum of 20 patient samples, like we said, you compare those with the values, the results you're getting from the reference method or CRMs based on the values that are supplied by the manufacturer. And then you are able to calculate your bias. So for bias, you can either compare to the total allowable error, or you can use sigma matrix. And in this case, anything above 3 sigma is okay. But the ideal is to go as far as 6 sigma. So how you calculate sigma is the total allowable error minus the magnitude of the bias that you would have gotten from your experiments. You divide that by imprecision. And the ranges for poor is anything less than 3. And 3 to 4 is marginal. 4 to 5, you are improving, you are getting to the good side. 5 to 6 is good, but above 6 is excellent. So that is the world-class performance that you also want to be getting to. And then method comparison studies. If you are already implementing 1704025 or 043 as well, and 15189, you will know that you expected to carry out comparison studies if you have more than one instrument running in your lab. So you want to carry out these studies to be able to prove and demonstrate that the results that we're getting from method A are the same or are similar to the results that we are getting from method B. So these are statistical analysis techniques that we are introducing to you, again, explained further in our 2 to 3 day method verification training. Then we also want to introduce to you a concept of reference interval verification. We know that this, for most people, you just adopt the manufacturer's reference range, but as a lab, you also need to verify the reference interval before adopting it. So for verification, you need a minimum of 20, and then you identify 20 healthy reference subjects that you then use their samples for, and you verify. If you want to do a full study, you go for 120 participants plus. Again, this is something that we should be able to explain to you in the full day course. And in doing this, there are practical considerations that you should be considering. You need to define your exclusion criteria for the reference subjects. For instance, if they are on medication or they have some disease state or they have a lifestyle, you need to define and check these before you can then say, okay, according to my criteria, this one is healthy and they are fit to participate in the experiments that I'm going to be carrying out. You also need to consider sex, that is gender, age, ethnicity, based on biological variations. We know that there are some analytes that are affected by age, for instance. There are some analytes that are affected by gender. So you need to define those beforehand and be able to exclude or decide on the criteria to include those in your experiments. You also need to document subject demographics for traceability so that when we are reviewing your data, we are able to then say, indeed, you worked according to how you had defined it. Okay, now let's move on to measurement uncertainty. Measurement uncertainty is defined as a non-negative parameter characterizing the dispersion of the quantity values being attributed to a measurement. Okay, so this is a classic definition that we got from the document International Vocabulary of Metrology, Basic and General Concepts and Associated Terms. So we normally refer to this as VIM3. VIM3, a document published by the Joint Commission for Guidance in Metrology. And this joint committee is, it includes organizations like the ISO, the ILAC, the IFCC, and many other organizations. So they set together in 2012 and came up with this definition. And of course, this was developed from the basic guideline that was published in 2008, the GAM document that we've been referring to earlier on. Why this matters? It matters because it is a requirement of ISO 17025 and ISO 15189. So whether you are in clinical labs, medical labs, or testing labs, or calibration labs, you cannot run away from this one. It is a requirement. So if you want to fulfill the requirements, you need to understand this and understand it thoroughly so that you'll be able to implement this in your laboratory. It enables meaningful results comparison. It supports clinical decision making. So it's not just a big calculation we are making and we are storing in files away, but we should be able to share with the users of the lab so that they are able to make meaningful clinical decisions based on the values that you are sharing with them. Okay. What we need to understand is that measurement uncertainty is not an error. It is a range of values based on the definition that we gave above. Okay, it is expressed either as a standard or expanded. Standard represented as a small u. So wherever you go, if you see a document that's quoting measurement uncertainty as a small u, you know it's a standard. As an expanded, a capital U is expanded. Okay, and the capital U is based on the coverage factor that would have been used to define confidence. Normally, we use factor K2 equals 2, which represents the 95% confidence interval. And then K3 will be your 99.7%, and K1 will be your 68%. So you need to be sure of what is being quoted there as the expanded. So under normal circumstances, we use the factor of 2. Again, it must be fit for purpose. Deciding on K1, K2, K3 is dependent on the intended use of the measurement uncertainty. Okay, What are the sources of measurement uncertainty? Sampling, you introduce uncertainties there based on sample collection, variability, patient preparation issues, container type, anticoagulant effect. So sampling may introduce uncertainties there. Pre-analytical includes sample transportation, storage, centrifugation. These are preparation samples, sample preparation issues. And then calibration, measurement equipment, the analysis that is used, the method, and the reagents. Okay, so there are two approaches to estimating measurement uncertainty. To the left is the GAM based on the 2008 document, 2008 document. And this one is normally used by calibration labs. Guys from the medical and the clinical normally don't get, they get confused when they see this document. But from the calibration lab, this is the reference document that needs to be applied. So for today, we will focus on the top-down, the empirical approach, which is the easier method to use for estimating measurement uncertainty. So we will focus on what we see on the right. And this is based on using existing performance data that would normally get from your IQC and EQA to estimate the total measurement uncertainty empirically. So we're basing on data that we've generated as a lab already. We are not using theory. We are not saying based on 1, 2, 3, this is what we expect. No, we are basing our facts on data that we've already collected over a long period of time. And the formula is the square root of the uncertainty due to bias squared and the uncertainty due to precision squared. Okay? Where U bias is the root mean square bias from PT performance over the different number of PT cycles that you would have participated in. And then the precision component, we get it from long-term reproducibility SD. And this is based on IQC. Typically, you'll be looking at data that has been generated over 6 months and above. But 6 months is optimal. And again, it's optimal for routine clinical or analytical use labs, and it's efficient, practical, and compliant with ISO 15189. So your ISO 15189 assessors, when they come, they see what you've done, 1, 2, 3, it's acceptable. Okay, so like I said, we are going to be looking at the top-down approach, the empirical approach. So you collect your IQC data over 6 months at each concentration level. So if you have low, medium, and high, so you collect data over 6 months. And then you calculate your U precision, which is the SD long-term, ensuring that the same units that you are calculating are the same units that you are reporting your results. Okay, so this will capture reproducibility. And then for bias, you are collecting data from at least 8 EQA cycles. So you need to be a lab that is participating monthly or more, because if you are going to be participating once or twice a year, it means you can go for 8 years without having adequate data to be able to calculate your MU, which may not be acceptable. Okay? And then once you've covered that, you calculate the root mean square, which is the square root of the first, the second, the third, up to the 8th bias squared, and you divide that by the number of data points that you have. And then you convert that to a an uncertainty contribution based on bias, which is the root square mean bias divided by square root of 3. And again, this assumes a rectangular distribution for systematic error component. Again, it's things that you are able to explain and we'll be explaining if you participate in our 2 to 3 day long training on method verification and uncertainty. And then next step is combining the two components, and that will give you a combined standard uncertainty. If you want to then go on and expand that, like I said, depending on the factor or the confidence level that you want to be reporting, at 68%, it's K1, the factor will be K1. At 95%, the factor will be K2. At 99.7%, the factor will be 3. So you then expand based on that. Okay, so this is an example that you can review and use to understand how you apply this. So this is a glucose example with IQC data that spans over 12 months. Like I said, 12 months will even be better. Minimum 6 months. Anything above that is better. Anything below is not good enough. Then you calculate your precision. Those are the values. And the EQA bias based on 8 cycles, like we said, minimum 8 cycles. You have those values. You calculate your root mean square and you get your values. And then you calculate the component, the uncertainty component based on bias. Again, like I said, based on the assumption that it assumes a rectangular distribution. It's that value which we calculated there divided by root 3, and then you get the value. Then you combine the two components. So the uncertainty component based on bias is 0.029. You square that one and add to the uncertainty component of 0.098 based on the precision. You square that as well. You add the 2 and you calculate the square root of that. You will then be able to get your combined uncertainty. If you want to expand it, like I said, you then introduce the factor K2 for 95%, and then you draw conclusions. I hope this is clear. And then applying measurement uncertainty to clinical decisions. This actually helps us to interpret results that are near decision limits and guides in patient management. So the example we have on the glucose of 4.2 plus or minus 0.3, the uncertainty plus or minus 0.3 millimoles per liter, and the reference range is 3.9 to 6.1 millimoles per liter. If you look at this and you expand, you will see that the top level for the 4.2 is 4.5 and the bottom level is 3.9. So the 3.9 to 4.5, they fall within the reference range of 3.9 to 6.1. Therefore, the conclusion is there is no diabetes action that needs to be taken because all the range of values fall within the normal range. And then something that is close to the decision limit, 6.0 plus or minus 0.3, the decision that will be made there, because the 6.3 is slightly above the reference range of the upper limit of the reference range, which is 6.1. So the conclusion that can be made there is that it's a pre-diabetes case, and you would recommend a repeat test to understand what's going on in the patient. So this is how you can apply measurement uncertainty in managing your patients or in advising doctors to manage their patients. So finally, as we carry out method validation verification, there is expectation to meet documentation requirements. We need to define in our quality policy, in our quality manual, the policies regarding method validation and verification. So if I'm coming to your lab, I need to see what your manual says in terms of the direction regarding method validation and verification. I also want to see your standard operating procedure, how your activities are governed in terms of what you've documented in your SOP. And you also need to have proper work instructions that are able to then give clear step-by-step tasks that need to be carried out that will then speak to your validation plan or verification plan. You need to have your data collection worksheets that will then be used to collect the data that you are generating. And all that will then determine what you'll generate as records and ensuring that your raw data is available for review as well. That will then be used to generate a validation or verification report that can clearly be traced. Now, the challenge with most labs is that you get nice statistical analysis done, and that is not traceable to raw data. And that's a big challenge. So we need to make sure that everything is in place. Okay, so the verification reports, the key sections, we looked at this before. We need to be defining the title, the purpose, the acceptance criteria that is predefined, the materials that are going to be used, ensuring that instrument IDs are specified, which lots did you use. If you're using the certified reference material, we need to be able to trace the data that you are getting to specific CRM certificate numbers, and the calibration records need to be clear. And all the raw data tables need to be filed nicely and traceable to the statistical summaries that we are getting. So like I said, in most labs, you'll find your nice statistical summaries that are not traceable to raw data. So we encourage you to ensure that all the raw data, including the repeat testing that you had to use, including the troubleshooting that you had to do, is kept in a file that can be reviewed for traceability purposes. You also need to then make comparisons with the set criteria that you would have set that is in your validation or verification plan and be able to draw conclusions whether or not it's passing and whether it is fit for purpose. And of course, it needs to be reviewed by a lab director or lab manager or somebody at that level to then sign it off and tell us when that is effective. Okay, so a bit on the requirements for the SOPs for validation methods. This is standard. I'm sure most of us are already implementing this, so we will not go much on that one. And then we also need to demonstrate ongoing method monitoring. Once we verify, we need to be able to show that the method that we are implementing in our lab is okay, it is fit for purpose. And you are encouraged to then ensure that we document our IQC activities in the form of Levi Jennings and apply Westcott rules when necessary. And if possible, go all the way to QC design based on Sigma matrix, which we introduced in a slide area. If your method is a Six Sigma method, then you can afford to run just one control because your method is performing very well. Just one control with one rule because you know your method is world-class as they define it. If your method is lower down, less than 4 or 3 sigma, you need to make sure that you are implementing tighter controls. If it means going all the way to 4 controls and multi-rules because your method is not performing well. So you need to be able to implement those. And of course, participation is in EQA or PT activities or interlab comparisons is mandatory. And all these are ways of demonstrating that your method is continuing to perform as per the verification status, and it is still fit for purpose. Okay. For my friends from the medical, clinical, that are implementing 15189-2022, this is a quick reference to the clauses that speak to the subject of the day. 7.3, 7.3, 7.3. And if you are from an accredited lab, you agree with me. This is the most problematic clause that labs are struggling with. If you go back and look at your NCs that you have been raised by your accreditation bodies, a good number of them are coming from 7.3. So we need to be able to understand this and understand this very well. So we also have a few case studies that we would want you to look at. We'll be sharing slides so that you get to practice more and more and understand how these things can be applied, the principles can be applied. This is an HbA1c example. We looked at the glucose example. It's similar to what we are also introducing here for you to be able to look at on your own. For the benefit of our friends from 17025, this is a pesticide residue example that you also can go through and understand in terms of validation of the pesticide residue in food testing. And then this again is an example of measurement uncertainty, checking for fit for purpose using a creatinine example. So if you do get time, please go through these examples so that you can understand. Okay, then now we look at the common pitfalls. Okay, let me see which one we can pick. All right, so one is setting acceptance criteria after seeing data. It's very common in labs that you already know what experiments you want to be carrying out. And then when you do get data, you see things are not passing. You then go back and say, no, we are not meeting the manufacturer's claims, but because of our conditions, we decided to use the total allowable error. Very common because you are not meeting the manufacturer's claims. But what we encourage is go back, do troubleshooting, see where you're getting it wrong, repeat the testing, and be able to meet the manufacturer's claims. In a number of cases, if you do that, you will be able to meet the claims without any problem. And then, okay, the measurement uncertainty calculated without long-term IQC data. In most cases, because you're under pressure to present this data, maybe you have an assessment coming in the next 2 months or so, and you've just introduced the method, you've not calculated, you've not accumulated enough data, you then end up using data that is less than adequate, maybe 2 months worth of data. It may not be as representative. So that's a common pitfall that we see around in labs, and we encourage that the minimum you should be using is 6 months worth of data. Okay, so what are the key takeaways? Measurement uncertainty is not optional. This is a requirement of both 15189 and 17025. So we need to understand this and understand this very, very well. And for guys outside the calibration labs, the top-down approach makes it practical and very easy to implement. So we can understand this and be able to calculate and implement this without a hassle. You need to define your criteria first. Don't wait until you see things failing, then you change the goalposts and say, this is what we are going to be doing. And then IQC sustains performance beyond the verification exercise. Okay. And then, of course, continual improvement, continual improvement, continual improvement. We are sharing again some references and further reading for those of us that would want to read further and understand the subject. Okay. And then finally, we'll be sharing, as usual, a link to a short quiz that you would want, you would participate in if you want to get a certificate. But today's subject is very technical. The quiz itself, I did look at it. It is not a walk in the park like we normally share. So I would really encourage you to go through the slide material, which we will be sharing, so that you are able to then get the best marks from the quiz that we are sharing today. Very technical. It requires a close eye and demonstration of understanding of the material that we presented today. And then, of course, if you want to get a certificate for attendance similar to the one we are showing to the right, you will be expected to pay a little something like $10. This will help us to continue delivering the webinars like we're doing. And we really appreciate the support we've been getting from the participants from day one. So you follow this link to then pay your $10. Once you've done that, send your proof of payment to info@CLISSQualityAdvisory.com and your certificate will be emailed to you to the email address that you used to register. Okay, so in doing this, we've noticed that we have some participants with very long names. So if your names, first name, middle name, title, and surname are greater than, have more than 16 characters, including the spaces in between, we suggest that you use initials like we did here because of the space that we have, and these certificates are automatically generated. So we're not able to then check and see if your names are able to fit within the given spaces. So if your names are too long, please consider using initials and maintain your surname. That way we'll still be able to identify that you are the one who participated. Okay, and then please do follow us on Facebook. We are very active on Facebook. We do share information about upcoming webinars. If there's any trainings, we advertise them through our Facebook page. We're also active on LinkedIn as CLISS Quality Advisory Private Proprietary Limited. And our email address is info@CLISSQualityAdvisory.com. We're also available on WhatsApp on these different numbers, +267, this is a Botswana number, 765405559. Or if you prefer to use our Zim number, Zimbabwe number is +26378125250. Or our South African number, +27783117631. So any of those, we will be able to get through to us and we'll be responding to you promptly, including the emails that you'll be sending through. We're also available on YouTube. I think all the material that we are sharing, we posting on our YouTube page. So if you scan the QR code here to our right, you will be able to go to our YouTube channel and please subscribe. Otherwise, that is the channel. We will then be posting all our recordings. So in case you missed the previous recordings, we've covered material on internal audits, management reviews, corrective action, risk management. All that is available in our YouTube channel. Otherwise, thank you very much. I'll accept questions for now. Like I said,